Hi everyone, this is Ali Nasser. In this video I'm going to talk about modeling of 2D laminar flow in pipe with a sudden contraction use Ansys. Before we start to simulate our problem in Ansys, let's give you a brief about this problem and how to simulate. In this simulation, we would to simulate a fluid flow from large diameter to small diameter of pipe, and the flow is going to a section or area called Vena contracta. Actually, Vena contracta, which means the point in fluid stream where the diameter of the stream is at least and the fluid velocity is at maximum, such as a stream out of a nozzle. Our case will be simulated in 2D dimension. Consider the flow is laminar and Newtonian fluid. Our objective will just study the flow characteristics to understand the flow feature from a fluid point of view, and also studying the flow through pipe with sudden contraction using fluent of Ansys or CFD tool. In the beginning, let me give you a very short brief about this problem. As we said, the flow through a pipe with sudden change cross section from large to smaller. The velocity of flow in conversion part of section 1 to section 2 of Vena contracta is increased due to continuity and pressure decrease in direction of flow accordingly to compliance with Bernoulli theorems. The significance of sudden contracting passage lays in the numerous industrial applications such as polymer processing of injection, modeling, biomedical, extrusion, thermoforming. Many applications we can observe these phenomena. Here is my geometry dimensions in this figure. As you see, the fluid will flow axial at the inlet D dimensions and then pass to small d of 15 centimeters, from 30 centimeters to 15 centimeters, and the upstream and downstream passage length has been set as 30 and 30. In our simulation, we consider the solution based on conservation form of governing equations for continuity and momentum for study flow field are given under governing equations. At the end, we're going to obtain or observe the pressure variation. And as you see here, at section 1 the pressure was high at the inlet, and then the pressure drop at section 2 of the Vena contracta region where pressure is minimum, and then the pressure will exit at section 3. We also going to observe the velocity variation, and as you see here at the section 1 inlet of fluid, the velocity was less at the inlet, and then velocity increasing at section 2 of Vena contracta region where the velocity here is maximum, and then expansion takes place because of jet and velocity reduce at section 3. That's all we want to observe during our simulation, and then let's go to Ansys to show how do this. Here is Ansys workbench. We need to go to solver of fluent. Just drag and drop here, and first step is build our geometry by right click and select modular geometry. Wait a moment till opening. Before we start our geometry, we need to define units. Select our units as centimeters. Our geometry, it will be just 2D sketch we can select XY plan. Click on the axis to be perpendicular on this plan XY, and then select new sketch. On new sketch, we can build our sketch by going to sketching. Our geometry is just two rectangle. We can select one rectangle here and another rectangle, and then we can define dimensions. But let me make constraints, coincident constraint for this point or this line with this axis to make the middle point of geometry in center of environment area or origin. And then go to dimensions to define our dimension. From general, this vertical length will be 30. You can define here V1 as 30, and from this axis to here it will be 15, half of 30. The remaining geometry dimensions from here to here, it will be this dimension, it will be 7.5, and all of this length it will be 15. It's defined as 15, and we need to define the horizontal length. This length as 30 as well. This also 30. That's all. We have defined all dimensions. We need to modify or trim this region. Going to modify, trim, cut this line, and make sure you cut it. This okay. We cut it both lines here, or one line. And now we need to make surface for this sketch. And to define surface, just go to concept. From concept, we can select surface from sketch and apply for this geometry. For this sketch, you can just click here and apply. Now it's assigned. We can finally generate. That's all here in geometry. Go to file, close design modeler, and make sure you see here right sign. That's mean everything is okay. Now we going to next step, mesh of geometry. Right click and select edit. Wait a moment till opening. Close this window. It's opening as you see here, and wait a moment to update like this. Just click on Z. We need to make some elements for edges, so we need to select, right click on mesh and insert sizing. We need to sizing by edges, so make sure you select your selection cursor is for edges. By right click here in environment area, select cursor mode and select edge. And for those edges, just hold control from keyboard, don't forget this. I will select for those 4 edges, okay, and apply here, and make sure here you can see 4 edges. And for type of sizing element, it will be in number of divided, not just select or double click here, or you can just double click here or click on this arrow to select number of division. Number of divisions will be we need to small number to get good result, so let's assume it will be 130 or 120 because this dimension is 30, so I divided to smaller number, like as you see. Let's select the remaining lines by go to mesh and insert sizing. For sizing, we can sizing this line apply, and double click here to select number of deviations. For number of deviation, let's select 150. It's okay, and this is okay. We can increase more. 200 is very fine. That's okay for this edge. The remaining edges, this one and this one, we need to go to mesh and select sizing to apply for these edges. Don't forget to hold control button from keyboard. Now we have 2 edges. For those 2 edges, we can define number of deviations as let's say 30. It's okay for 30. Again, insert sizing for what is the remaining this line again. We need to define number of deviations for this line. Let's say 60 or 70. Okay, make sure you have select all edges. I make sure here all edges, it's okay, everything is okay. Now we need to make mesh for all surface, face mesh. Right click here and select face mesh, insert face mesh for this face, apply. That's all. After this, we need to define boundary conditions for inlet and outlet and the wall. So first, make sure your cursor on edges. For these edges, we consider as inlet of flow. Right click and select create named selection, and just type as inlet. Define as inlet. Now we define this as inlet, as you see here. We need to define this as outlet. Right click, create named selections, outlet, and make sure we select outlet. Okay, hold your control button from keyboard and select the remaining edges to define as wall boundary condition of this pipe. Right click on any edges, name selection, wall. Let's make sure we already here 6 edges. That's okay. We need to generate to assign and update our mesh and boundary conditions. Just click here for generate and wait a moment. Here is our meshing. It looks finer, so we can just go to file and close meshing. After this, we just need to update our mesh by right click and click on update. Wait a moment to update your meshing. Okay, and now step number 3 is setup. We need to define our setup. Right click and select edit as you see. To raise your precision of calculation, just double click on precision and okay. Wait a moment till opening. We will go in the order. First step, it will be general. As we said in introduction, the flow will be laminar. So just double click here in general and select steady. Make sure your setup is steady. Then go to model. Just go to model, double click and select viscous laminar. double click again. From viscous laminar we need to define K epsilon for 2 equations. That's enough for our case to just determine pressure and velocity. Okay. After this we need to define material. Double click on material, select air, edit air. We are going to add our fluid as water. So select user define database. Fluent database. From Fluent database you can find water at the end of materials. Here we can select this one and copy, close. Now we define our fluid as water liquid. Just click close. Then after we define material, we are going to assign material by going to cell zone. Double click here on the zone, select surface, edit. From here we select our material as water liquid. Now we assign it our material. It's just select OK. After this we need to go to boundary condition. Double click on boundary condition and select inlet. From boundary condition, edit to define at inlet our velocity. Here velocity magnitude, it will be 0.5 meter per second. That's all for our boundary conditions. And then we need to go to initializations. Double click here on initializations. We need to make sure our initialization is a standard. From standard we need to compute the inlet from inlet, and after this we just click initialize. After initializations we need to go calculation. Here from calculation, that's just expand and you can find solution animation. From solution animation, double click here for solution animation. We need to define our parameter we want to observe, like pressure and velocity. Just a new object and select contour. From contour, our contour will be pressure in its name. It's okay, it will be for all surface. And after this we need to save this and close. Now pressure contour is defined. Now another contour for velocity. Select contour, name it as velocity. Here select contour velocity for all surface. Save and close. Okay, don't worry, we didn't save, and we'll save later. You can initialize this bottom. After this we need to go to calculation. From calculation we just add the number of iteration to get a good result. It depends on your geometry. Our geometry it's about 60 centimeters. Let's say it will be 300 iterations. Calculate. Wait a moment while it's calculating. Actually it will take 2 minutes or something like this. It's going to finish. Yes, it's actually finished now. Just okay. And from file, close Fluent. I save it. Wait a moment. Everything is now, it's okay. Just go to results, edit results. From results we are going to obtain our velocity and pressure variation. Let's be perpendicular as you see here. We need to insert new contour. Okay, from contour we can select symmetry 2 and number of contours as you wish. We can consider as 100. Apply. As you see here, this is the pressure contour. We can also see the velocity contour here. Apply, like you see. Also, we can create a streamline. Let's create streamline. It's okay. From streamline, we need to uncheck contours, and we can select inlet. Start from inlet, and let's increase the number of point to say 100. And I want to try a symbol of fish as a fluid flow fish. Okay, we can see velocity here. Let's animate this stream, and we need to slow a little bit. It's okay. As you see here, this is contraction. We can increase the number of samples. This is not enough. We can see 200. Apply. It's okay. We can change to symmetry 2. Look, you can select as you wish. Set as an inlet, no problem. Direction forward, you can select backward again. And let's make fast a little bit here. This is the phenomena of Vena contracta. Okay, let's make chart for this. To create chart, we need to create a line. Go to insert from location. We can select line, name it as line. It's okay. Line here from point 1 to point 2. Point 1, it will be our origin. It's here 0 0. So this distance, it's 30 centimeters. If we just say minus 0.3 to define in meter to 0.3. Let's apply. Look at our line from here to here, and our sample we can define as 100. Apply. This is our line. Now we need to show our chart. Just to go to chart from here, select our insert new chart. Okay, our chart will obtain its data from a line. So go to data series. From data series, we need to go to location. For location, just select line 1, and from line 1, let's apply to see here the solution for pressure variations. It was maximum and then drop to minimum. And if you want to change the variables, you can go to y-axis. Let's select instead of pressure to be velocity. Apply. This is the solution of pressure. It was list, and then going to maximum velocity at Vena contracta regions, as we said before. So that's all about our simulation. Let me give you a brief about conclusion. Our conclusion about this simulation: the fluid through a contraction is increase in pipe, and result is increase in velocity. Consequently, the pressure drop greater than a value for equivalent street pipe. Velocity increases due to continuity, and pressure decreases in direction of flow accordingly of Bernoulli theorem. That's all about our simulation Vena contracta or sudden contraction inside the pipe. I hope this is useful or helpful for you. My regards, Ali Nasser.